we begin with the next topic. Successive differentiation. Successive differentiation. So you remember the formulae for differentiation? What is d by dx of constant? 0. What is derivative of x raised to n? Derivative of root x? Derivative of 1 upon root x? So to begin this chapter, we will have to list out all the formulae. D by dx of constant is 0. D by dx of x raised to n is n into x raised to n minus 1. D by dx of root x is 1 upon 2 root x. D by dx of 1 upon root x is actually d by dx of x raised to minus half, which is minus half x raised to minus 3 by 2. D by dx of 1 upon x is minus 1 upon x square. D by dx of log x is 1 upon x. D by dx of e raised to x is e raised to x. D by dx of a raised to x is a raised to x into log a. Then we have d by dx of sin x is cos x. D by dx of sin ax is a into cos ax. D by dx of sin of ax plus b will be, sin's derivative is cos of ax plus b into the derivative of this. So it is again a cos of ax plus b. D by dx of cos x is minus sin x. D by dx of tan x is sec square x. D by dx of sec x is sec x tan x. D by dx of cosec x is minus cosec x cot x. D by dx of cot x is minus cosec square x. D by dx of sin inverse x is 1 upon root of 1 minus x square. D by dx of tan inverse x is 1 upon 1 plus x square. This will be the minimum set that we will require. If you know it, fine, otherwise make a note. And of course d by dx of u into v is u dv by dx plus v du by dx, and d by dx of u upon v will be v du by dx minus u dv by dx whole thing upon base square. These are the minimum formulae we will require to start with the next topic called as successive differentiation. Okay, make a note and then we will start with the topic. First problem, if y equal to ax plus b upon cx plus d, prove that 2y1 y3 equal to y2 square, 3y2 square. Now here the notation changes. Whatever we call it as dy by dx up till now can also be termed as y1, can also be written as y dash. So the same problem can also would have been asked as 2y dash y triple dash equal to 3y double dash square. Could be. Right? So the meaning is same in the even throughout this particular chapter, and henceforth we can follow any of these notations. It means the same thing. Dy by dx is y1 is y dash. So when he says 2y1 y3 equal to 3y2 square, we don't have any choice but to find out all the things and substitute in LHS and RHS. So as y is ax plus b upon cx plus d, what will be y1? We are required to differentiate. It is v du. This is as good as u by v. So v du cx plus d into a minus u dv ax plus b into c upon cx plus d bracket square. V du minus u dv upon. So when we expand, acx and acx cancels. What remains in the numerator is ad minus bc upon cx plus d bracket square. So far so good, because from numerator x got eliminated, right? Second derivative y2. Now ad minus bc is constant. What will be derivative of 1 upon cx plus d bracket square? It is minus 2 upon cx plus d bracket cube into c, right? So it will be minus 2c into bracket ad minus bc upon cx plus d bracket square bracket cube. That will be y2. And what will be y3? It will be minus 2c into bracket ad minus bc is constant, and the derivative of 1 upon cx plus d bracket cube will be minus 3 upon cx plus d bracket raised to 4 into c. That gives us 6c square ad minus bc upon cx plus d bracket raised to 4. So LHS is 2y1 y2. So it is 2 times ad minus bc upon cx plus d 2y1 y3. ad minus bc upon cx plus d bracket square into y3 is 6c square ad minus bc upon cx plus d raised to 4. That gives us 3 into 4. I am writing 12 in that manner. ad minus bc bracket square c square upon cx plus d bracket raised to 6. I have written it purposely because I have already seen this y2. So this can now be written as 3 times minus 2 into ad minus bc into c upon cx plus d bracket cube square, because we have already calculated y2, and then this will be simply 3y2 square, which is RHS. So not a difficult problem, not of the engineering level also, but still these type of problems are asked in the exam. Prove that, and just to check your differentiation capability, right? That is the first one. And now the trick that one can play here can be a different way. Let us take this down, then we will see how can we solve it in a bit different manner. So this is the crude way which we used to solve even in 12th. We can say that instead of writing y2 in terms of y1, once you find y1, write it as cx plus d bracket square y1 equal to ad minus bc. And then this is also function of x. This is function of x. Now differentiate. So you will get cx plus d bracket square y2 plus 2 times cx plus d into c y1 equal to 0. Right? So we are not just finding them one after the other. We will try to. So we have already got y2, y1. Now what? Cx plus d can be cancelled? Yes. So we have cx plus d y2 plus 2c y1 equal to 0. If we again differentiate, what do we have? Cx plus d y3 plus c y2 plus 2c y2 equal to 0. So we get cx plus d y3 equal to minus 3c y2. But it doesn't actually simplify our task. What we need to do could be substituting y2. That's very funny. y2 equal to minus 2c y1 upon cx plus d. Right? We multiply both sides by y2, but once we substitute RHS and once we write it as y2, because our answer demands for y2 square. So out of that 3 we have already got. So I say that multiply both sides by y2, but on the left hand side it is cx plus d y3 into value of it is minus 2c y1 upon cx plus d equal to minus 3c y2 square. And we get the answer. So some trick. This will be faster also, but you will have to work it out in this manner. So cx plus d cancels. You have minus 2c y1 y3 equal to minus 3c y2 square. So c cancels, comes plus, proved. So all the problems we will have to start differentiate it once, adjust them, and we will not be finding them simultaneously. From y1 we won't be finding y2. We will have everything expressed in terms of the previous differentials. Second problem. If y equal to 1 minus x square bracket raised to half, show that 1 minus x square d2y by dx square minus x dy by dx plus 2x plus y equal to 0. So we start with y equal to 1 minus x square raised to half, and so dy by dx will be, so it is actually root x, 1 upon 2 root x, so it is 1 upon 2 into 1 minus x square bracket raised to half into derivative of 1 minus x square is minus 2x. So 2 cancels and I write it as minus x upon y, because 1 minus x square raised to half is y only. So we get y dy by dx equal to x. Again differentiate it by u into v, it is y into d2y by dx square plus dy by dx into dy by dx equal to 1. So we have y dy by dx what happened? Yeah, this is minus 1, huh? This is minus x, so minus 1, huh? But what should we do now? Because he wants dy by dx also. So again the same trick, 1 dy by dx we should substitute and 1 we should keep as it is. So 1 dy by dx is minus x upon y dy by dx is equal to minus 1. So it will be y square dy by dx minus x dy by dx and then it will be equal to minus y, and that is a problem. Where is 2x gone? Because this term I got this also, and I am still missing with this 2x. What's going on? No, it is his printing mistake. It is only y. It is only y. It's not there only. Right. And so we get it as 1 minus x square d2y by dx square minus x dy by dx plus y equal to 0, proved. He mixed up with the two problems. The second problem is in the same way, and now it is into sine inverse x, and then it comes with 2x plus y. And now I want you to solve this. It is just to be solved on the same lines. So it right now begins with u into v only. So there was a multiplier sine inverse x, and so dy by dx will be 1 minus x square raised to half. Derivative of sine inverse is root of 1 minus x square 1 upon plus sin inverse x into, it will be 1 upon 2 times 1 minus x square raised to half into minus 2x. So this is simply 1 minus sin inverse x upon 1 minus x square raised to half. Now what happens is I am unable to write y, dy by dx in terms of y. So first of all I will multiply by 1 minus x square raised to half dy by dx equal to 1 minus x square raised to half minus sin inverse x till here. And looking at the answer, I will say that let us multiply by it once again. So this becomes 1 minus x square dy by dx equal to 1 minus x square minus 1 minus x square raised to half sin inverse x. So I have multiplied by 1 minus x square raised to half and again multiplied by 1 minus x square raised to half. Actually I have multiplied by 1 minus x square so that I can get y. So it is 1 minus x square dy by dx equal to 1 minus x square minus y. So it is 1 minus x square d2y by dx square plus dy by dx into minus 2x equal to minus 2x minus dy by dx.
So basically minus x sin inverse x
minus x sin inverse x minus x sin inverse x. So this will be xy. Good enough. So minus 2x minus x dy by dx minus y. And it is proved only then. We missed out this x here. We missed it here, so we missed it. If y equal to capital A e raised to minus kt into cos of pt plus c, prove that d2y by dt square plus 2k dy by dt plus n square y equal to 0. If y equal to P sin mx plus q cos mx. Prove that y2 plus m square y equal to 0. P and q are constants. If y equal to e raised to ax into sine of bx, prove that y2 minus 2a y1 plus a square plus b square y equal to 0. If y equal to tan inverse of sin x, prove that d2y by dx square plus tan y into dy by dx bracket square equal to 0. N square and what is n? N must be k square plus p square asal mein. N square is p square plus k square. Now just have a look at it. Second problem is simple. We just can't put it in terms of y. When you differentiate, dy by dx will be pm cos mx plus minus qm sin mx. But single differentiation will change sin to cos, cos to sin. You differentiate it once again, you will straight away take minus m square common and it will be y. So second is simple. In third problem or in the first problem, you find y1, there will be u into v, okay, and e raised to minus kt into minus sine of pt plus c into minus p is first term, plus a e raised to minus kt into minus k into cos. So that second term can be replaced by y. So one term will still remain. And when you differentiate it once again, that will again turn out to be. So that has to be managed in that way. In the sixth problem, e raised to ax into sin bx, it will be e raised to ax into cos bx into b. So the term has changed. But plus it will be e raised to ax into a into sin bx, that will be ay. One cos changes to sin, that we can't replace, but the other one we can. And here it is typical. It is dy by dx is tan inverse, the derivative is 1 upon 1 plus x square. So it will be 1 upon 1 plus sin square. What is 1 plus sin square? Cos square. So it becomes sec h square. Okay. So dy by dx comes out to be sec h square x. Sec h square x you again try to write in terms of tang and then try to proceed. Or whatever way. Looking at his answer, looking at his answer, he is getting tan y. That means that he has written it as tan y equal to sin x and using u into v. Or rather tan y derivative will be sec square y dy by dx equal to derivative of sin x is cos x. So he is going in that way. Otherwise he can't get tan y if we continue with y, right? These are comparatively simple. For the fourth one, when we find dy by dx, it will be a e raised to minus kt into minus p sine of pt plus c plus a e raised to minus kt into minus k into cos of pt plus c. And so we write it as minus ap e raised to minus kt sine of pt plus c minus k into y. Is that okay? So if we find d2y by dx square, it will be minus ap into bracket e raised to minus kt into cos of, rather p cos of pt plus c plus e raised to minus kt into minus k into sine of pt plus c minus k dy by dx. So it becomes minus p square y, first term. Second term becomes minus minus plus pk into a e raised to minus kt sine of pt plus c minus k dy by dx. And so what we do is we will substitute this thing from here. It will be ap e raised to minus kt sine of pt plus c. So ap e raised to minus kt sine of pt plus c will be substituted. This is to be taken on the right hand side, to be substituted as minus dy by dx minus ky. This k is already there. It is minus dy by dx minus ky minus k dy by dx. So it becomes minus p square y minus k dy by dx minus k square y minus k dy by dx, and it is proved. This substitution is important. This is to be substituted in terms of dy by dx. So it will be d2y by dx square plus 2k dy by dx plus p square plus k square y equal to 0. That is n square. Right? And have you completed that last one? No. Okay. What was that? It is y equal to tan inverse of sin x. And we thought of starting from tan y equal to sin x. One way that we have thought of was directly going for dy by dx as 1 upon 1 plus sin square x into cos x. That is, we differentiate it directly. What is 1 plus sin square? 1 plus sin square is cos square. So this becomes cos x upon cos square x, and so it is 1 upon cos x. then I can write it as cos x dy by dx equal to 1. And so it is cos x into d2y by dx square plus derivative of cos x is sin x dy by dx equal to 0. What was to be proved? 1 minus x square. No. What was to be proved? d2y by dx square plus tan y dy by dx bracket square equal to 0. Okay. So we divide by cos. So d2y by dx square plus tan x dy by dx equal to 0. And using these two, we know that sin x is dy by dx and sin x is tan y. Sorry, we know that from here sin x is equal to tan y and cos x from here is 1 upon dy by dx, and therefore tan x is tan y dy by dx. Substitute. You can always go with the other formulation also, like tan can be written as sin upon cos, and then cos can be written as under root of cos can be written 1 plus sin square and all that, but this will be simpler just to determine tan x and proceed. So it becomes tan y dy by dx and dy by dx. Yes. So this was not successive differentiation. Successive differentiation is now the one which we are going to start. Like it is number 1. Y equal to e raised to ax. See it is very simple. Dy by dx, we will write it as d of y, where d is d by dx operator. What will be the derivative? It will be a e raised to ax. Differentiate it again. D square of y is a e raised to ax into again differentiation of this. So it is a into a e raised to ax. It will be a square e raised to ax. D cube y is a cube e raised to ax, and so on. And so we get the formula as nth derivative of e raised to ax is a raised to n e raised to ax, and this nth derivative is successive differentiation, and we can put any value of n, it should be valid. Some formulae we will derive, some we can write directly. This we could have written directly. What will happen if y is sin of ax plus b? What will happen if y is sin of ax plus b? Then d of y will be a cos of ax plus b. But we don't want cos, we want sin. Can we do it in that manner? Because the next derivative will be that d square will be replaced by minus a square. That one can very well prove. Hmm? One more derivative will give us, matlab d square y will be minus a square sine of ax plus b. Yes, that is true. So you will get a replacement ke d square will get replaced by minus a square, but there is no replacement for d, whereas we want to write it for d raised to n, and we don't know what is n. So can you suggest me something?
Under root 1 minus cos I square.
That will lead to lot of trouble. Can this be written as a sine of ax plus b plus pi by 2? So sine of pi by 2 plus theta will be sine pi by 2 cos theta plus cos pi by 2 sine theta. Cos pi by 2 is 0. So sine of ax plus b will vanish. But first term is sine pi by 2 cos. That is this. And for this now I can write it as it is a square sine of ax plus b plus 2 pi by 2. It is sine of pi plus theta is minus sine theta. Right? And so we can generalize and say d raised to n of sine of ax plus b will be a raised to n sine of ax plus b plus n pi by 2. And whatever is the formula for sine, same will work for cos. It is nth derivative of sine will be a raised to n ax plus b plus n pi by 2. Okay, make a note. There are so many formulas, almost 8 or 9 of them, and problems will be to find nth derivative of, and that too there will be a generalization of the product u into v is there and its nth derivative. Nobody will ask you derivation, of course, but these formulae should be known through and through. Third one, when y is a raised to x. So differentiation of a raised to x will be a raised to x into log a. Actually a raised to x we interpret it as e raised to x log a. So it will be the same formula as e raised to x. Okay, you differentiate it once again, a raised to x second derivative, it will be a raised to x into log a square. Like that, nth derivative of a raised to x is a raised to x into log a raised to n. And the fourth one is interesting. Y equal to ax plus b raised to m. Now the things begin. So what is d d of ax plus b raised to m. What is the derivative, Aniket? What is the derivative of ax plus b raised to m? M into ax plus b raised to m minus 1 into derivative of ax plus b a. Right? So we differentiate it again. D square of ax plus b raised to m. What it will be, Nikita? What is the derivative? This m remains. What is derivative of this term? What is the derivative? M minus 1 ax plus b raised to m minus 2 into a, and original a is there. So this is the derivative. So it comes out to be m into m minus 1 ax plus b raised to m minus 2 into a square. Fine. Now everything will depend on what is n. There will be cases when n is less than m, n equal to m, and n greater than m. So do we have answer for any one of these directly? You got the question? Now I am coming to three cases, because when we are finding nth derivative, in this case it will depend on what is n. Suppose n is equal to, matlab one case is n equal to m, second case is n less than m, third case is n greater than m. Now we already know that if we have x raised to 5, then its fifth derivative will be constant and sixth onward are 0. So we know that if n is greater than m, if we have ax plus b bracket cube, its third derivative will be constant, fourth onwards will be 0. So for this n greater than m, answer is 0. We don't have to discuss it separately. Okay, n equal to m. So we consider case 1. N is equal to m. Now as I generalize, I will find that nth derivative of ax plus b raised to m will be m into m minus 1, etc. Now see, when it is 2, it is up to m minus 1. When it is 1, it is up to m minus 0. So when it is n, it will be up to m minus n minus 1. Barabar? What is the power? When it is 2, it is m minus 2. When it is 1, it is m minus 1. So it will be ax plus b raised to m minus n. And when it is first derivative, it is a, second derivative a square. So it is nth derivative a raised to n. This is what we get. And we are talking about case a, n equal to m, n less than m. This formula works correctly for n less than m. Perfect. And when n is equal to m, when n is equal to m, it will turn out to be d raised to n of ax plus b raised to n, because n is equal to m. So this will be m into m minus 1, etc. up to n minus n minus 1. So it will be up to 1. This will be ax plus b raised to 0, a raised to n. And so we get the formula as n factorial into a raised to n. Same thing. Nth derivative of ax plus b raised to n, we can write it as, I have written it in m manner because m is equal to n, and so it is m factorial or n factorial, one and the same. This is one case. Done. This remains the formula for n less than m. And case 2, when n is greater than m, nth derivative of ax plus b bracket raised to m is 0. Right? Make a note. Even if we remember formula for n less than or equal to m as this and substitute, it will still work out to be the same thing. So we don't have to worry. This is a crucial case when it is greater. Fifth, when y is 1 upon ax plus b. Now differentiation of 1 upon ax plus b will be minus 1 upon ax plus b bracket square into a. If I differentiate it again, second derivative of 1 upon ax plus b, then minus 1 is already there, right? 1 upon ax plus b bracket square derivative will be minus 2 upon ax plus b bracket cube. 1a is there and one more a, so a square. I am not cancelling the signs because I want to generalize it properly. If you cancel, then it creates a problem because it is going to be alternate plus and minus. Generalization for a raised to n is fine, but this way it might be a problem. So once again, d cube of 1 upon ax plus b will be minus 1 into minus 2 is there. It is minus 3 upon ax plus b bracket raised to 4 into a cube, which I can say that it is nothing but minus 1 cube 3 factorial upon ax plus b raised to 4 into a cube. So can it work here? Yes, it is minus 1 square 2 factorial upon ax plus b raised to 3 into a square. So looking at all these, now can we write nth derivative? It is 1 upon ax plus b. It will be cube hai to minus 1 cube, square minus 1 square, so it is minus 1 raised to n, cube then 3 factorial, square then 2 factorial, so into n factorial upon ax plus b. It will be n plus 1 into a raised to n. So it's the key to generalization. Don't mix up with those signs and all. It will create chaos. Because then it is difficult to write what should be the power of minus 1. And then I want those who have written this to generalize for ax plus b bracket raised to minus n. You can write it as 1 upon ax plus b raised to m and then do it. That is fine.